We can also test the normality of a set of data involving paired samples. Like here, we have 3 columns. The first column is for the student number. The second column is for the pretest. And the third column is with the post-test scores. Let's say these are examination scores of students. Usually, if you would like to determine whether there's significant difference between the pretest and post-test scores of students, we usually use the paired samples t-test. But that is only if we have established already that the difference between the pairs are actually forming a normal distribution or even closely similar to a normally distributed set of data. Because if this set of data here or the difference between the pretest and post-test scores will not give us a normal distribution, then we cannot use the paired samples t-test, but we are going to use its equivalent non-parametric test, the Wilcoxon-signed rank test. So for here, before we go to our analysis, of course, again, we have 3 columns here. These are, we have 90. Okay, 90 respondents or students. And of course, if you're going to proceed for our variable view, we can see that for the first column, because it's just a representation of students by number, we call it just nominal. And the pretest here, you can even label it pretest scores, as well as post-test scores. Both of them are in scale because we are dealing with scores. Okay, so after you are done with that, you can proceed to the data view, and we can also structure a certain pair of hypotheses so that we could, of course, tell later if what is the correct option to take. Let's consider these 2 hypotheses. We have our H sub O, or our null hypothesis, stating that the set of the difference between pairs is not significantly different from a normal distribution. Or in other sense, it means that the set of difference between pairs is closely similar to what is a normal distribution. Okay? If we are a researcher and we would like to use paired samples t-test, we would like this null hypothesis to be retained. In short, we want this null hypothesis not to be rejected. If this would be rejected, of course, let us have this alternative hypothesis. The set of difference between pairs is significantly different from a normal distribution. And if we later will reject our null hypothesis, this alternative hypothesis will then take charge. That would mean that we will be using the non-parametric test equivalent to paired samples t-test. Of course, when do we know to reject? The rejection here, of course, is still if p value or the significance value is less than 0.05. That is, of course, we are 95% confident with our data. Okay, so if we are rejecting the null hypothesis, that means, again, the difference between pairs are not normally distributed. But of course, again, we would like our H sub O or null hypothesis to be retained for us to use the paired samples t-test. But if we are not to achieve that, then of course we can still use the non-parametric test with the Wilcoxon-signed rank test. Okay, so how do we analyze now? Now let's start with the calculation. We are going to start with solving for the difference. Okay, because we will not be testing the pretest scores nor the post-test scores in testing of normality. For testing for the normality of paired samples, we need to add another column which tells us about the difference. Of course, in your Excel, you can always subtract the pretest scores to post-test scores or vice versa to get the difference. But here in SPSS, you can also try to use this. Okay, click transform, and let's compute a certain variable. Again, let's click transform and compute variable. This will allow us to compute a certain target variable. Let's call it the difference between pairs. So you can even say difference only. Others will use residuals, but let's just have it difference between pairs. And the numerical expression is, let's have pretest scores, input here, subtract post-test scores, and place it there. This will be the computation. Now, it doesn't matter here if your result later on will be negative because, of course, usually the post-test scores will be greater than pretest scores. You can even interchange the two. You can have post-test scores and then subtract pretest scores if you would like to. But later, we will just be checking the test for normality using these differences. So after that, and after you're done with that, Once you click OK, you would see that the fourth column here will be labeled with this, and the entries here are the differences. Just like this. When you click OK, okay, this would be your output. So you can simply return to your input area or interface. As you can see, these are the difference between pairs. Since we have pre-test minus post-test, that's why we have negatives. But then again, you can just interchange both of them. Doesn't matter about the signs because we'll just simply, just for normality, we're just simply testing this. Okay, so as you can see, we have until here. Okay. Now, there are a lot of ways before we analyze this. There are a lot of tests. We have the graphical representations. We also have other statistical tests, just like Kolmogorov-Smirnov, Shapiro-Wilk, and others. In this case, we'll just be using later on the Shapiro-Wilk. Now, the Shapiro-Wilk is useful for smaller numbers, but there are also some claims that it's not also good to really look into that and just simply focus on the QQ plots. But just for this time, let's just focus on Shapiro-Wilk. The Shapiro-Wilk is good for other references. Will say less than 50. We have less than 100, even less than 200. And since we have 90 here, so we will be using that. Other references will also say less than even 2,000. The Kolmogorov-Smirnov is for large, what do you call this one, sample sizes. So again, let's proceed to Shapiro-Wilk. And this is how we do it. Okay, we'll be proceeding to analyze. Click analyze. When you hover to your descriptive statistics, and you will have here your explore button. Again, we'll have analyze, descriptive statistics, and explore. Once you click that, you will have this dialog. Now, we will be placing the set of data we'll be testing for normality here in our dependent list. It will not be pre-test, post-test. It will not be pre-test. It will also not be post-test. What we'll be testing here for normality is just the difference between pairs. So click that, click this button, and you will have your independent list. Now, no need to apply something here. It's just already okay with that. And go to plots. When you click plots, you may unclick stem and leaf. Some of us, or some of the suggestions also the histogram, but let's just simply click the normality plus with test here. Okay, and for this we have a lot of graph later. We will have the QQ plot as mentioned earlier, but we'll just be again focusing on the Shapiro-Wilk. If we're going to click continue, that's set to go and clicking OK. But of course, you can also visit statistics here. For your descriptives, again, that's 95%. That's the default. You can change it if you would like to, but generally we'll have that. You will also have your options here, but again, simply clicking by plots, you go to OK. Once you click this, you will have your result just like this. In your output area here, this would be the results. So you have your summary here, your descriptives, and we will be proceeding to this test of normality. As I mentioned, you also have your plots here, okay, and you could see this one. We also have another explanation for that probably later, but let's focus here on Shapiro-Wilk. We have here Kolmogorov-Smirnov, again for large quantities, and we will be using this. Focus on the significance value or p-value here. We have 0.578, or that's 0.578. Going back to our hypothesis earlier, or our decision for rejection, we are going to reject our null hypothesis when our p-value or significance value is less than 0.05. But this is too large or larger as compared to 0.05. That would mean that we will not be rejecting our null hypothesis because this is greater than 0.05. So we fail to reject our null hypothesis. And going back to our data earlier, this would mean that this set of data here for pre-test and post-test scores are with their difference, as the difference between pairs is significantly closely similar to our normal distribution. That would mean that we will be using the paired samples t-test in testing the significant difference between the two sets of scores. Again, the result would be the set of difference between pairs is not significantly different from a normal distribution. That is how we test the normality for paired samples. We have two set of scores, but they are actually paired samples. See you in the next video.